Hello, McMath here. Welcome back to another math video. This one we're talking about inverse functions and relations. Again, thank you for watching, and let's take a look at what we got here. So first off, an inverse function. Two functions are considered inverse functions if and only if one function has the element AB, the other one will then have the element BA. Pretty much the idea behind this is that the x and y coordinates are going to switch each other. So whatever's the x in the 1 and the y in that same function is then switched around. That same number will then be now the x, and then the x value will be the y. So it's that whole switching of the x and y's is related to the whole idea of finding the inverse of a function. So find the inverse of a function, very straightforward. If it's like f of x or g of x or h of x or something like that, you rewrite it so it's y and x. So then if it was f of x equals blah blah blah, you write it as y equals. And then you switch the x and y's. So wherever you saw y, rewrite it as an x. Wherever you originally saw an x, rewrite it as a y. Now you're solving the new equation for that y value. That will then be the inverse of whatever the function is. Now, important to remember that functions have to pass your vertical line test. So just because we're switching around now, just because it wasn't originally a function, because it passed the vertical line test, doesn't mean its inverse will also be a function. So determining if it actually is a function itself, the inverse will only work if the original function passes now the horizontal line test, which is the same idea as the vertical line test. If you can draw a horizontal line through any point in the function and hits the line more than once, then its inverse will not be a function. The inverse will still exist. The inverse will just simply be a relation. You might have to restrict the domain in order to make sure that the inverse can be written as a function. If your function passes the horizontal line test, then its inverse will also be a function, and there will be no restrictions. So first off, we have the function f of x equals 2x minus 5. So if we really quickly think about how that line looks, 2x minus 5 will look kind of like this. Linear line will always pass the horizontal line test. We don't have to worry about linear lines then. So the way we find our inverse is we're going to rewrite it as y equals 2x minus 5. And now we're going to rewrite our y as x and rewrite our x as y. So it becomes x equals 2y minus 5. And now we're going to solve for y. So if we're trying to isolate y, we need to move everything else around. So we're going to add 5 and make it x plus 5 equals 2y. And then we divide by 2. So we get y equals x plus 5 over 2. So our notation, if the inverse is a function, would be f negative 1 of x. That's our inverse notation. And there'll be x plus 5 over 2. That's simply all we have to worry about. Again, linear lines will always pass a horizontal line test. Linear lines also have domain being all real numbers, range being all numbers, so there are no restrictions on domain or range for the inverse function itself. Now, quadratics, like f of x equals x squared plus 1, well, will look something like this right here. It's our U shape. And as you can see, it won't pass the horizontal line test. So while we can find the inverse will not be a function until we restrict the domain for it. So we still start off by saying y equals x squared plus 1. We still switch the x and y, so now it becomes x equals y squared plus 1. And now we solve for the y, so we have to subtract the 1 over. X minus 1 equals y squared. And then we take the square root. Or technically, again, when we do the square root in algebra problems, it should have plus or minus the square root of x minus 1 equals y. So this is the reason why it will not pass the whole plus or minus aspect. So what we can say is, we can say that if we're dealing with the dimensions for the x can determine, we know first off x has to be greater than or equal to 1. We know that much first off the bat. So here we know that our relation, we have our plus or minus square root of x minus 1. We do know the x's, this domain has to be x such that x is greater than or equal to 1. Which if you look back at it, that was the original range. Now, the range here, in order to make sure that we actually have a function, if we just restrict the range for this, such that the range is only going to be talking about, we'll say now values for y, such that y is greater than or equal to 0, we can then say our inverse relation is the positive square root of x minus 1. That could be a function there. Or, if we restrict our range to be y such that y is less than or equal to 0, we can then use our negative square root of x minus 1. So all simply depends on which one we're dealing with for this particular example. The restrictions are going to depend on whether or not we can write as a function. So still go through the algebraic process, just recognize technically that the plus or minus square root of x minus 1, whenever it's a quadratic, is not an inverse function, it's just an inverse relation until you restrict something. Okay, so that's dealing with the quadratics. This one right here, the cube root function, which we're going to talk about how to graph that in a later video, is going to look something kind of like this, the general shape. It's going to be kind of like that. So a cubic function will always have a horizontal, it'll always pass a horizontal line test, similar to the, cube root function, similar to the linear function. It's only really going to be your quadratics that don't really pass it, or some other more complex examples. And we'll take a look at some of those. But for the most part, we're dealing with basic inverse function ones. The more complex examples, it becomes hard to solve for it algebraically, which is why we're not really going to consider it. So we still write it out the same way. Y equals cube root 7x plus 5. Still becomes x equals cube root 7y plus 5. Now for this one, we can't subtract the 5 just yet because it's stuck inside the cube root. So we have to get rid of the cube root. So we get rid of the cube root by cubing both sides. We get x cubed equals 7y plus 5. Now we can subtract the 5 over, get x cubed minus 5 equals 7y. We can divide by the 7, and we're going to get the inverse now is x cubed minus 5 over 7. And there's our cube root function. There's our inverse function. Still the same general process, switching the x and y's, moving things around. Like I said, it's only really the quadratics we're worrying about right now, which don't pass horizontal line tests, that we have to talk about restricting domain or range or anything like that to make sure that we actually have a true inverse function. Now, if we're given two functions and asked to verify if they're inverses, well, this is only true if both of their compositions, so the composition of, like, let's say f of g and then g of f, those are the two functions, have to result in the identity function x. If it doesn't result in x when you do your composition, then it's not going to be an inverse. Theoretically, you also could just work with one function, find the inverse of that function, and see if it matches up. That's also another way you can do this. That might be a little bit quicker depending upon the problem itself, but I'll show you the composition, and then I'll show you the other way. So the way the composition works is we would do f of g first. So we would do 3 times 1/3 x minus 3 plus 9. Well, when we distribute the 3, we get x minus 9 plus 9, and that equals x. Typically, once you get one of them to work, the other one is probably going to work as well, but you should always still go through the same process anyway. So then g of f, the other composition, will be 1/3 of then 3x plus 9 minus 3. Now you distribute the 1/3, we get x plus 3 minus 3. And then the 3's cancel, leaving us also x. So yes, this is a inverse. Like I said, you could have also theoretically just worked with the f function, make it y equals 3x plus 9, rewrite it as x equals 3y plus 9, subtract 9 to get x minus 9 equals 3y, divide by the 3, get 1/3 x minus 3, and you see that's the exact same function here, so then you can say, yeah, they're inverses. So again, your call. The mathematical way is doing the composition f of g, g of f. A shortcut would be just to work with the one function, find its inverse. So we have f of x equals 4x squared and g of x equals 2 square root of x. So if we're doing f of g, be 4 times 2 square root of x squared. Well, we get 4 times 4x which is 16x, and no. It's not exactly x. There can't be a number in front of it. It can't be negative x either. That's a common misconception. It's getting negative x. Like, all right, that's fine. No, it's got to be positive x. There can't be anything else. Again, if you worked with trying to rewrite the one function, y equals 4x squared, would become x equals 4y squared. So you get 1/4 x equals y squared. So when you do your square roots, you get the 1/2 x equals y. Technically plus or minus, but again, we're just dealing with only, I guess, the positive one here as a function being defined here, and we notice it's 2 times square root of x rather than 1/2 times the square root of x, so that's where the difference is. Had they used a half there instead, this would be a yes. Alright, so last one. So I'm just going to use the shortcut for this one instead of doing your f of g, g of f. I'm going to work with g. So g is y equals the square root of x plus 1 over 2. So we have to square both sides to cancel it out, because this then becomes x squared here. I forgot to switch it. My apologies. Y plus 1 over 2. So you multiply by the 2 to make it 2x squared equals y plus 1. Subtract the 1. 2x squared minus 1 equals y. That's the same thing here, so you can say yes. So like I said, the more mathematical way is to do f of g, g of f, verify they both work out as x. Shortcut would be to work with one function only and find its inverse, and see if it matches with the given the other function. Totally up to you how you want to go through it. In terms of saving time, you probably want to deal with one function versus the other. But please remember the actual formula, the f of g, g of f thing is a vital thing to remember when you start talking about like calculus and inverses in calculus, or trying to find inverses of functions that technically you really can't find an inverse for. It starts getting a little more important to remember that. So hold on to that knowledge. Alright, so that's all I got for you today. Again, thank you for watching, and I will see you next time.